Okay, so this is the second video with the topic 5.3 about concentration and time. And there's a whole set of reactions, or there's a whole set of formulas for first order reactions. And so we're looking at second order reactions. Second order reactions can be one reactant making products or two reactants making products. Two reactant making products is much more complicated than is AP chemistry. So we're just looking at one reactant, but happens to be second order. So of course the rate law would look like this. And then what would that look like with the calculus applied to it? And basically it looks very similar to our first order reactions, but the formulas for first order reactions, but now it's 1 over. It's the reciprocal of the concentrations. And very similar, I would choose, these are on your formula sheet. I would choose this version if the question was asking me for time. I might choose this version if the question was asking me for the amount at a certain time down the road. Similar to what we just looked at for first order, second order will form a straight line if we graph 1 over the concentration versus time. So this is another way that we can identify if a reaction is first order or second order. So we could look at a table of reactions, experiment 1, experiment 2, experiment 3, look at what happens to the rate as I increase the amount of reactants, or now I can graph data at different times, and if the natural log versus time is a straight line, it must be first order. If the inverse 1 over concentration versus time is a straight line, it must be second order. And that's a very common type question where you will be getting data and then it will ask you, is it first order or second order? If I think you have one of these on your homework, if you do, then you do need to actually graph it that way. The easiest way to do that is probably not on your calculator, but to go ahead and open up a Google spreadsheet and look at those graphs. If this was an AP test, they would be giving you these two graphs and then asking you, based on the data, what do you think, first order or second order? This one, we know it's second order. The rate constant for the reaction is this. If the initial concentration in an enclosed vessel is 0.0500 molarity, what is the remaining concentration after a half an hour? Pretty straightforward here. You can use, obviously either one, but I'm going to use 1 over the concentration of A at time t equals KT plus 1 over the concentration of A at time 0. And so now just start plugging in what I know. K is 0.542, 1 over molarity times seconds. Time is a half an hour, but since the rate constant is in seconds, I need it to be in the units of seconds. So 0.5 times 60 times 60 is 1800 seconds, plus 1 over the concentration of A at the beginning, which was 0.0500 molarity. Plug in those numbers and notice the seconds are going to come out. Molarity is going to be in the denominator. So 1 over the concentration of A at time t is going to equal 0.995, 1 over molarity. Take the inverse of that and get 0.00100 molarity equals the concentration of A, or whatever chemical it is at time t. Here's a multiple choice question. You can give this one a try, pause, try, and then restart. For a certain reaction, A to products, a plot of ln versus time produces a straight line with a slope of negative 3.0 times 10 to the negative 2 inverse seconds. If it's ln, natural log of A, it produces a straight line, I know it's first order. So, yes, it does produce first order kinetics. Yes, the rate constant is the opposite of the slope, The initial concentration was 1. There's nothing in this prompt that makes me believe that the initial concentration would be 1. So I'm going to choose answer choice B. 1 and 2 are true. So 0th order, right? What the heck does 0th order mean? Well, 0th order, I don't think that's actually written on here. 0 order means that the rate would be equal to just a constant, that the initial concentration of the reactants does not matter when it, or doesn't even factor into the rate. It actually doesn't slow down as the reaction continues. This is the integrated rate law for this. That's not on your equation sheet, which means you won't need to use it. This is just hitting home that if it is 0th order, that means that the slope never changes, that the reaction never slows down, that it keeps going at the same rate. This graphic here just organizes all of the formulas for 0, 1st, 2nd order. Remember that 0th order really isn't on the equations table. 1st order and 2nd order are. You should know what makes a straight line. You should know that the slope is negative k versus positive k. And so moving on a little bit, half-life. So half-life is something about the rate of a reaction, right? If it has a short half-life, that means that it reacts quickly. If it has a long half-life, it reacts slowly. So obviously, somehow these concepts are related. Exactly how is what we're going to be looking into. There's half-life formulas for 1st order reactions and 2nd order reactions. 2nd order reactions you do not need to know. But the 1st order reaction formula is on the formula sheet because this is often how radioactive decay is generally a 1st order reaction. Just depends on one reactant. And the length of a half-life is how long it takes for half of a substance to decay or react. If the question is asking you for the length of a half-life and it gives you a rate constant, you can use 0.693 over K to figure that out. If you're given the length of a half-life, you can use this formula to find K. Sometimes you'll be given a table and it will say at the beginning you have 5, and then at 10 minutes you have 2.5, and at 20 minutes you have 1.25. And so from that you would deduce that, oh, the half-life for this is 10 minutes. And then you could go and use this formula. So here's another sample question using this half-life concept. Sample exercise 14.9. This is that reaction of that chlorobutane, right? Chlorobutane reacts with water. It's a first order reaction. And it says, from this graph, estimate the half-life for the reaction. So let's see, if I start with 0.1 molarity, when do I reach 0.05 molarity? And let's see, 340, something like that. I could also, verify that by looking when would it reach the next, when would it go down by another half? And that would be 0.25. And yeah, what would 340 plus 340 would be 6. Now this looks a little bit more like 7, but we're estimating here. Sure. So I'm going to go with 340 seconds. And then B says, use the half-life to calculate the rate constant. Pretty straightforward. It's a formula that you have on your formula sheet, 0.693 over K. So that means I'm going to just rearrange this before I plug in the numbers. 0.693 over the half-life. So 0.693 over 340 seconds. So the K would be equal to 0.0020 and the units would be inverse seconds. Pretty straightforward. It's all of these formulas are intimidating, but you are given the formulas, so you don't need to memorize them. And it's plugging in and solving. So pretty simple algebra.